cover the Sparks Notes version of what you need to know today. And so we went over all the different ways to make amino acids on Monday. And so today, what we're going to do, we're going to start off by looking at all these different reactions like the Helmholtz-Zielinski, the Strecker reaction, aminomalonate synthesis in a little bit more detail, in that we're going to try a couple of problems. And so something that it would be wise to do, if you haven't done it already, is print out a copy of the amino acids. So print amino acid handout. And it's in the chapter 25 module. You'll see something that says amino acids Klein. And I have it here. You can hear me rattling the paper, okay? So I have a list of them. So I have most of them memorized, but just to be sure I don't make any mistakes along the way. So let's start out by finding out the reagents that you would need to make each of the following amino acids using a Helmholtz-Zielinski reaction. Well, if you think about the skeleton of an amino acid as looking something like this, like what do they all have in common, right? They all have an amino group. So I'll just put squiggle like this because we only know racemic syntheses except for one that we're going to talk about at the very end. And then they all have some kind of R group here, okay? So when we're doing the Helmholtz-Zielinski reaction, if we want to make, let's say we want to make leucine. Well, if I write down the structure of leucine, which looks like this, and again, we're talking about an achiral synthesis. So when I write a squiggle like this means racemic, when you write a squiggle line like that instead of a dash or a wedge. And so if you remember, a leucine has an isobutyl group, right? This would be categorized as an isobutyl group, as an R group here. And so what would we need to start with? Well, basically all you're doing is taking a carboxylic acid and you're installing the amino group in this position. And so all we need to do is take this carboxylic acid. So I'm just going to draw the skeleton of the carboxylic acid we need like this. Then we're going to install a bromine on it. So let me just move this over a little bit like that. We're going to install a bromine on it. And I'll write down the conditions in just a second here. So we're going to install a bromine like this. So again, that's going to be racemic. And then we have our carboxylic acid. And then the last thing we're going to do is we're going to hit it with excess ammonia, excess NH3, and that is going to give us our desired product. So if you're thinking to yourself, well, does that mean all I have to do is just look at this part here and say that is the carboxylic acid I'm going to need? That's absolutely right. So the first step is going to be phosphorus tribromide and bromine, so PBr3 and Br2. Didn't leave myself a lot of room here. And then the second step is going to be H2O to hydrolyze the acid bromide. So there you go. That's how you would make you'd make leucine using the Helmholtz-Zielinski reaction. So now if we think about, and again, this is a racemic compound, so you can either write here racemic, but again, it's implied by this squiggle bond here. So let's say we wanted to make alanine. Well, alanine's R group, right? R just equals a methyl group. Okay, the R here was an isobutyl group. And so what are we going to need for our amino acid this time? Or sorry, our carboxylic acid? We just need the 3 carbons of propanoic acid. Then we're going to install the alpha bromine, so phosphorus tribromide and bromine, followed by water. That puts the bromine in at the alpha position. And then that bromine is susceptible to an SN2 with excess ammonia. So ammonia for excess, there we go. And so we're going to end up with alanine, which is this very compound right here. And of course, it's going to be racemic. So we can put here racemic. And that's a little bit about the Helmholtz-Zielinski reaction. But I think that the next question, if I'm not mistaken, I looked over them briefly this morning, it also involves the Helmholtz-Zielinski reaction. So it just says here, if each of the following carboxylic acids was treated with phosphorus tribromide and bromine, followed by water, and then excess ammonia, what is the amino acid that's going to be produced? So it's going to be the exact same thing for the second one. So I'll just copy and paste this. And paste it right here. And so again, it's the same thing for both of them. All you're going to do is you're going to install an amino group at the alpha position, which I just put a little red dot on there. So for the first one, we're going to end up with leucine. You can probably tell that right away. So we're going to end up with something that looks like this. So for the first one, we end up with this compound, which is racemic leucine. And for the one on the bottom, we have that isopropyl group coming off the end. So we're going to end up with valine. Okay, so valine looks like this. Your R group is just an isopropyl group. So there's our amino. Let's go back. Where was I? Somewhere back here. I'm sure I lost everything. Oh, yeah, it's all gone. All right, so let's try this again. So step 1 is going to be phosphorus tribromide in bromine. Step 2 is going to be water. Step 3 is going to be excess ammonia. There we go. So we end up with leucine for the first one. There we go. So we got leucine. Okay, and again, that is racemic. And then so for the next one, if I just copy and paste, try to save a little bit of time since I lost all my hard work, I'll end up with this, and all I have to do is delete this spinach here. There we go, and that's going to be racemic alanine. So we'll move this over here. Just write alanine. All right. And again, you can see that little red dot that I put here in the alpha position. So with the help of Zielinski, if you start it with a carboxylic acid, all you do is put an amino group in the alpha position, and there you go. You go in and you identify your amino acid. All right. So that's a little bit about the Zielinski synthesis of amino acids that we covered last class. All right, so let's move on to the amidomalonate synthesis. And this is a variation, I guess, on the ethyl acetoacetate reaction that we looked at way back in chapter 21. And so if we want to make isoleucine, so if you go over and look at the chart of the amino acids, you'll see that isoleucine actually has 2 chiral centers in it. Don't worry about the chiral centers. We're just going to make an achiral version of it. And so if we think about isoleucine, what does isoleucine look like? Well, don't even know if I have enough room to put it on here, but if I'll put ILE for isoleucine, and then I'll just draw the structure here. So isoleucine has this bit here. So we have our amino group down here, and then we have our carboxyl group up here like this. So if this is isoleucine up here, it turns out that these 2 carbons come from the starting material in the amidomalonate synthesis. And so our alkyl halide is going to come from this portion here. So that means the alkyl halide that we're going to need is going to be 2-bromobutane, or you could call it sec-butyl bromide, either way. Okay, either one is totally fine. So now that you've seen a little bit of the retrosynthesis, let me show you what I mean exactly. So we're going to start out with our ethyl acetoamidoacetate. So we'll start with that. Here's our nitrogen, which has its acetyl group on it, like this. Okay, so the first step is going to be to treat it with sodium ethoxide. And then we're going to need the alkyl halide, which we decided was 2-bromobutane. Okay, so we do the SN2, and we end up with this. So just bear with me here. And then all shall be revealed in the end. So we end up with our sec-butyl group, which looks something like this. And then we have our nitrogen here with our acetyl group like that. Okay, good. Now that we've got that, remember, it's these 2 carbons from the amidomalonate that are going to show up in your amino acid, right? So this is going to be your carboxyl group. This will be the nitrogen. And then this, of course, here, that's going to be your R group. So all we have to do in the end is take it, and we're going to heat it up with some aqueous acid, and we'll cook it up like that, and we end up with isoleucine. So we're going to end up with this. There we go, like that. And remember, so the H3O plus, right, it's going to hydrolyze this amide bond. It's going to hydrolyze this ester. It's going to hydrolyze this ester, and then it undergoes a decarboxylation where you lose CO2. So carbon dioxide is lost in this process, and that's one of the reasons why it's irreversible, because you form a gas. So we end up with isoleucine, and the 3-letter abbreviation for isoleucine is ILE. The 1-letter abbreviation is I. Yes, this is a chiral center, but don't worry about that chirality center. We're just going to do a racemic synthesis. Okay, so now that we've got that in mind, we figured out that the R group for isoleucine was a sec-butyl group, and with alanine, our R group is just a methyl group. We've seen that already. And so now our alkyl halide is not going to be something like sec-butyl bromide. Our alkyl halide is just going to be methyl iodide or methyl bromide or methyl chloride. And so I can actually copy and paste some of the material here. So I'll just take this and we'll just move it down here just in the interest of time. So let's paste this. So I have the same starting material every single time. I have my sodium methoxide every single time. And now I'm going to change my alkyl halide to methyl iodide. So, and if you use methyl bromide, methyl chloride, they're both fine as well. And so now we end up with our acetamido, diethyl acetamido malonate. So we have our methyl group, and then we have our acyl group on our nitrogen, and then all we have to do is cook that up with some acid, and we hydrolyze the whole darn thing. We do our decarboxylation, and we end up with racemic alanine. You know, I noticed one thing that I made a mistake on something here on the first one is if the hydrolysis happens in aqueous acid, that's acidic condition. So technically I should have written this as the cationic form of the amine, right? The acid would be protonated and the amine would be protonated as well. So we'll do that down here, NH3 plus, like that. So this is alanine. ALA is the 3-letter abbreviation, and A is the 1-letter abbreviation. I'm not going to go through all of the valine synthesis, but the R group for valine is an isopropyl group. And so in the first step, okay, so if I paste this back in here, the first step, your alkyl halide is going to be isopropyl iodide or isopropyl bromide, doesn't matter. I'll just use isopropyl iodide like that. So then you're going to end up with the isopropyl group attached in the middle here. So the artistry is getting pretty crummy here. Okay, so there's my isopropyl group. There's my acetylated nitrogen. And then after you heat that up with aqueous acid, I'll just put here, you're going to get valine. And the 1-letter abbreviation for valine is V. You guessed it. There you go. So that's a little bit of the amido malonate synthesis. I think the next question is in the exact same vein as well. It just says here, an amido malonate synthesis was performed using each of the following alkyl halides. In each case, draw and name the amino acid that was produced. Well, the first two are not really worth going over in detail because for the first one, and for the second one, we're using isopropyl chloride, and we actually saw this in the previous one. We used isopropyl iodide, and we know that after treatment with H3O plus and heat, we end up with valine. And for the first one, it's methyl chloride, and we did that one as well on the previous slide. We just used methyl iodide. So in that case, we know that after, I guess I should put the chloride if that's what they're saying here, but it's the same thing. Okay, so methyl chloride, methyl iodide, doesn't matter. Anyhow, so then after treatment with aqueous acid and heat, we end up with alanine, okay, and these are racemic. So let's try the next one, which says 2-methyl-1-chloropropane. So if I paste everything in here, and let's get this over here. So we've got 2-methyl-1-chloropropane. Let's see here. So we've got 1-chloropropane, and then we've got 2-methyl. We'll look at that. It's an isobutyl group, all right? So you can see where we're going with that we are going to end up with a leucine. So if I put that in here, and again, you can take your time to draw the whole thing out, but you can clearly see that after we treat this with aqueous acid and heat it up, you're going to end up with leucine, and the 1-letter abbreviation for leucine is LVA. All right, give me a thumbs up if you follow me on the acetamido malonate synthesis. Everybody with me on the idea? We kind of did the same thing twice, and then the Helvold-Zielinski. I only got one thumb up here. Okay, 2. Okay, so hopefully most people are following along here. So that covers those. So that's the first 2. Now the next one we're going to look at is the Streca. You know, you can't call it Strecker. It's got to be the Streca, right? So that one you start with an aldehyde. You have an aldehyde, and then you're going to treat it with ammonium chloride in sodium cyanide. So I don't know if I can squeeze it in here. NaCN. This doesn't look very pretty. Anyhow, and then you end up with an amino nitrile. So that looks something like this. So if we have something that looks like that, alpha amino nitrile, like that. And then after treatment with aqueous acid, then you end up with your R group is going to be over here, and then we'll put NH3 plus, right? Because you're in aqueous acid, right? So you're going to end up with the protonated form in the end. So if you think about it, these two carbons, okay, this carbon here comes from the cyanide, okay? That's where that one comes from. And so the other carbon, meaning this one here, comes from the aldehyde, okay? So hopefully that makes some sense. So if we wanted to make methionine, so if we write out the structure of methionine, and I'll see if I can squeeze it over here on the far right. So methionine looks like this. So I'm just going to draw it with a squiggle bond because we're talking about racemic syntheses here. So if we want to make this compound, okay, kind of the way I did this when I was a student is like this. I don't know if it's considered cheating or not, but this is kind of my Sparks Notes version, is I'd write this carbon comes from the cyanide, right? And then this carbon, the red one here, that's the one that's attached to the aldehyde. And so that's how I kind of figure it out. So then I'd say, well, then I have this, and done. And that's my aldehyde, and then I'd be off to the races. So that's kind of my version of the retrosynthesis of how I used to do these when I was a student. So I would start out with the aldehyde. So let's just write it out here. So we'll have, oops, missing a sulfur there, Mr. Dion. So 1, 2, there we go. Like that. We're going to treat it with ammonium chloride and sodium cyanide. There we go. And then we're going to end up with the alpha amino nitrile. So I'm going to try to write it the same way they do in the book, just to make things a little simpler. So there's the hydrogen that came from our aldehyde. And here's our R group. So we have CH2, CH2. That's not very pretty. CH2, CH2. There we go. So 1, 2, and then we have our sulfur, and then we have our methyl group coming off like this. And then when we take that and we treat it with H3O plus, so some aqueous acid, and we cook that up, then we end up with our methionine. So let me just delete some of my retrosynthesis here. And there we go. That's our final product. It's just like that. Okay. If you didn't follow me, check it out. We'll do it one more time. This Mr. Dion's version of the retrosynthesis. So let's say you wanted to make histidine. Okay. I'll do this one in blue just to kind of separate it from the first one. So you started by writing the structure of the amino acid. So we have our carboxyl group here. Remember, your amine is going to be protonated because you're hydrolyzing an acid in the end. And then for histidine, you have to put the imidazole ring. This is what this is called, is imidazole. So you've got this, and then you got a nitrogen here. There we go. Okay, so there's histidine. Okay, now that's the protonated form of histidine that we get at the end. So like I told you, it's this part here. That's where the aldehyde is going to come from. Maybe that didn't work. My box didn't fit on there quite right. So let's draw it like this. Okay, this part is where the aldehyde is coming from. Okay, so what is your aldehyde going to look like? All you have to do is draw your carbonyl like that. Okay, it's just, you can draw it upside down like this every time. Maybe that'll be easier. I don't know. Anyhow, oops, not very pretty. There's my 5-membered ring like that. Okay, so there we go. So now we're going to treat it with ammonium chloride and sodium cyanide. We're going to end up with the alpha amino nitrile. So we put our amino group, our nitrile group, our hydrogen, and again, that comes from our carboxyl group. Then we have CH2, and then we have our imidazole ring, which I ran in a room. So come on, iPad, do me a salad here. So then we have our histidine ring. So end up with something that looks like this. There we go, like that. There we go. And then we treat that with aqueous acid, and we cook it up, and we end up with our alpha amino acid. So for phenylalanine, I'll let you do this one on your own. If I want to make phenylalanine, So does somebody have a question? Okay, so phenylalanine is just like you have alanine, but then you have a phenyl group. So if this is alanine, phenylalanine just means you have a phenyl sticking off instead of a proton for one of your R groups or for one of your hydrogens. So there you go. So there's phenylalanine. So if I want to make phenylalanine, my aldehyde is going to come from this portion right here. So I'm going to start out with this aldehyde. So end up with this guy like this. And all we have to do is just say to get from here, step one, it's going to be ammonium chloride and sodium cyanide. And step two, it's going to be aqueous acid and cooking, heating it up. And there you go. So that's a little bit about the Strecker. Let's try another one that involves the Strecker synthesis. So the next one is just giving you some aldehydes and asking you, well, what would you end up with? Okay. The first one is acetaldehyde. So if you read it, the structure of acetaldehyde, it's the same thing as ethanal. That would be the systematic name. So we have this compound. Now, another way to think about it is to draw it like this. Okay. So then if you draw it like this, then you can see this part gets incorporated into, like, your amino group ends up being here in the end. So your R group is just a methyl. So that means you're going to end up with what? You're going to end up with alanine in the end. So I'll just put here, rotate 180 degrees, okay? And you end up with the acetaldehyde like this. So step one is going to be to make the alpha aminonitrile. So we have ammonium chloride and sodium cyanide. And then we end up with the alpha aminonitrile like this. All right. Have our R group here. There we go. And then we cook that up with some aqueous acid. Go take a break or something while it's boiling. There we go. And so we get a racemic synthesis of alanine. The next one is 3-methylbutanal. So if we have 1, 2, 3, 4 carbons like this, and then we have a 3-methyl, you can see that that's an isobutyl group is what we're going to have as our R group here. And so we're going to end up with leucine. So we're going to treat this with ammonium chloride and sodium cyanide. That's going to give us the alpha aminonitrile. This guy here. And our R group is going to be the isobutyl group, like that. There we go. And then we're going to hydrolyze that with aqueous acid. So aqueous acid, heat, cook it up, and we end up with some leucine. So it looks something like this. There we go. All right, there we go. So for the last one is 2-methylpropanal. So if you have propanal, it looks like this. So one, no, that's even worse. Okay, 1, 2, 3 carbons. Okay, so that's an isopropyl group. And so after the 2 steps, so step 1 is going to be ammonium chloride in sodium cyanide. Step 2 is going to be H3O plus and heat, and that is going to give you valine. So you're going to end up with, there's your protonated amine, there's your carboxyl group, and there you go. All right, so that's a little bit of the Strecker synthesis. So again, this is Strecker. And in case you didn't pick up on it, this intermediate here, this is called an alpha amino nitrile is what we call that, okay? An alpha aminonitrile. All right, oops. Let's keep going. Another question before we get into some new information here today. So look, I'll kind of show you what we expect in terms of asymmetric hydrogenation, where you end up with a chiral amino acid. So this is kind of all we do. So it says identify the starting alkene, okay, the starting alkene. So you don't have to start from the very beginning. So here's what you do. Let's say you wanted to make L-alanine, okay? So what you would do is you would write the structure of L-alanine. Maybe I'll use a black pen. There we go. So you'd write the structure of L-alanine, which looks something like this. So we have our group coming out like that. And we're going to make the protonated form of it like this. Okay, because the last step is going to be to treat it with aqueous acid. So here's what you do is all you have to do is this, is your retrosynthesis is you're going to start with the same compound, okay, where you have the carboxyl group here, but now you're going to have a double bond here instead of a single bond. And if that's a double bond, that means that this carbon is sp2 hybridized. So you're going to have a straight bond down like this to your nitrogen, but it's going to have an acetyl group on it. Remember, AC stands for acetyl. Okay, you're going to have an acetyl group on there. So that's the starting material that you're going to end up with or start with. So all I'm going to do is take this, come on, just copy it. And I'll put that as my starting material to prove it to you. Okay, so here's my starting material. All I'm going to do is this, is I'm going to say H2, so for hydrogen gas, and I'm going to write chiral catalyst. Okay, you don't have to write it the big gaudy structure of that chiral catalyst that I showed last class. So what that does is it does the hydrogenation to give you the chirality that you want, but you still have the acetyl group. So you have your bond to nitrogen now is a wedge. So you only have one stereoisomer, but you have the acetyl group on there. And so in order to make the carboxylic acid, to make the amino group, to remove the acetyl group, what you do is you hydrolyze it in base. So you hydrolyze it step 1 with sodium hydroxide. That breaks the amide bond, but that gives you the free amine, and then you protonate it by using aqueous acid, and that's the synthesis. That's all there is to it. So let's say you wanted to make valine. All you would have to do is this, is you would start it with a double bond here, okay? Put NH acetyl, and now your R group, you just have those two methyl groups coming off, right? This is going to make an isopropyl once it's hydrogenated. So you're going to say H2 chiral catalyst. That's going to give you the chiral compound, but you're going to have the acetyl group on there. And so you're going to hydrolyze it first with base, and then you're going to do a workup with aqueous acid, and that's going to give you the compound. So kind of running out of space here, but you get the idea. So it looks something like this, and there you have it. So now you have chiral valine. All right. So for the next one, for isoleucine, I'll let you do that one in your own free time. But again, it would be the exact same vein. You just have the double bond in place. You have the acetyl group on your nitrogen, so NHAC. AC stands for acetyl. And now you're going to put you're going to make sure that when this is hydrogenated, you end up with an isobutyl group in the end. There you go. So that's going to be your starting material. And then you just move forward like that. All right. So that brings us to section 25.4.